Welcome to Chemistry 221. I am so pleased to have you here, and I'm really excited that you wanted to spend your time here learning this material. Very, very cool. Chemistry 221 is the beginning of the majors level chemistry courses, and we're going to start in right here with a lecture over Chapter 1. And if I give these in an actual face-to-face environment, you could also watch those. This is kind of like a compact, kind of all-in-one kind of overview to the first chapter of Chemistry 221. And the website for this class, mhchem.org/221, is your gateway to all the things you're going to see. And probably if you're looking at this video, you've already been there, but just in case you haven't, that would be great. Now, I have a note on there. It says, get the Chem 221 Companion and a lab notebook. The Chemistry 221 Companion is basically everything you need for Chem 221. It has all the problem sets. It has lectures, lecture slides and stuff that are printed that you can use to write down notes at the same time. It also has practice problem sets and concept guides and sample quizzes and exams. It's pretty cool. You can purchase it through Mount Hood Community College. You can also download it and print off the parts you want. Either way is totally fine, but it is a good way if you have the companion, you've got everything you need. Now, if we're doing labs face-to-face, then you will need a lab notebook. A lab notebook is something that you'll need to write notes down and stuff, make sure you're good to go. If you're watching this, maybe we will have labs, maybe we won't. It's hard to say. But if we do have labs, make sure you bring a lab notebook. So without further ado, let's get into what chemistry is all about in this first chapter of Chemistry 221. We have to ask ourselves, of course, what exactly chemistry is.
How would you describe chemistry?
Chemistry.
Kemi.
Jag vet.
Är det här kemi?
Or is this chemistry?
So all of that video showed different examples of how chemistry plays an important part around all of us all the time. And it can be the traditional chemist in the lab. It can also, though, be people like scuba diving. And you wouldn't probably think about it while you're scuba diving, but in order to breathe underwater, you have to understand where the oxygen comes from, how the oxygen is made. The material of your suit has to be made in a chemistry lab and stuff. So chemistry is all around us all the time. And hopefully this video kind of jolted you a little bit, makes you think about how chemistry affects you in your world and like what's around you right now at this very instant.
Chemistry is the science of matter, of its properties, and of its transformations. All matter is made from about 100 elemental forms, the elements. Intrinsic to matter is energy. The waves of the ocean are energy made manifest and obvious. But energy permeates even the most subtle interactions of matter and is fundamental to chemistry.
When someone asks me what chemistry is all about, I try to tell them in more or less layman's terms that chemistry is really about the transformations of matter and energy. And the matter part people usually dig because, chemistry, atoms, molecules, stuff like that, protons, whatever, okay, no problem. But people a lot of times don't think about the energy. Without energy, nothing really happens. So if you just study the matter, that would be kind of boring. But the energy is important. So chemists are going to focus on not only the matter, but the energy of system as well. And that's why the waves at the ocean are perfect, because you see the matter, the water molecules, going up and down with the waves. On the other hand, those waves wouldn't be there unless the energy was propelling them forward, which is kind of cool. The name chemistry came from an ancient Egyptian process for embalming the dead. And I think it's pronounced chemia, but I could be totally wrong, okay? And so chemia, which was later metallurgy and stuff like that, has always had a little bit of kind of an arcane kind of a feel around it because, ooh, these people that are doing dead things and stuff, are chemists, right? And of course, now in chemistry, we see ourselves as more than just a cult and stuff. But anyway, that's kind of where it is. So sometimes chemistry people have a little bit of a leeriness about it, and I understand. However, realize it's because of the old school ways. The Egyptians used to embalm people in pyramids and stuff, and anyway, put them in pyramids. And now, of course, chemistry makes cell phones. So the transitions have been quite dramatic, shall we say.
Matter is made of atoms. When two atoms of the element hydrogen are bound to a single atom of the element oxygen, they form a molecule of water. Atoms and molecules are amazingly small. Because atoms and molecules are, in a practical sense, impossible to see individually, scientists often depend on models when working with and discussing them. A single drop of water contains more than 2.5 billion trillion water molecules.
One thing that's really wild about chemistry is how small the bottom pieces are, the smallest pieces. So like there was an example of water, all right? And all of us today have consumed water in one way or the other and stuff. Humans need it all the time. However, the water molecule itself is really small, and they had that massive number of molecules in just a little bit. My favorite example with water is that if you have a teaspoon of water, all right, you have more molecules of water in a teaspoon of water than there are teaspoons in the Atlantic Ocean. Now, the Atlantic Ocean is big, all right? If you've ever seen it, and you're standing in Florida or whatever, you can't see Europe or Africa and stuff. It's a long ways out there. So there would be a heck of a lot of teaspoons. However, if you have a teaspoon of water, you have more molecules than you have teaspoons of water in the Atlantic Ocean. So water and all molecules, pretty small. And we're going to need special techniques and models to talk about them, because otherwise we would just get lost in how small they are. And as we're going to see, we'd also get lost in how many of them we have at any one time. Chemistry has gone through transformations. So we saw it, we said earlier about the chemia, the kind of Egyptian version and stuff, and then it went to an Arabic version, and alchemy, which is kind of chemist's dark cousin we don't like to talk about. But anyway, Boyle was considered one of the first chemists, but he called it chemistry with a Y, and now chemistry is the modern version. So you can see how the name chemistry has changed over. Also, chemistry is not limited to just one group of people, all right? Like it started arguably in Egypt. It then went to the Arabian Peninsula and stuff. Europe and definitely Africa has had lots of transformations. Of course, gunpowder in China and stuff. I mean, it's an international study. It's not focused on one group, and that's kind of exciting too.
Matter changes. Atoms and molecules are in constant motion. Heat increases this motion. The amount of motion dictates how well atoms and molecules can hold on to each other. The less motion there is, the better the hold, and the more solid the matter. When liquid water is cold enough, its molecules arrange in a particular structure and turn to ice. When heated, the vigorous motion of liquid water molecules separates them from one another, and they become an invisible gas.
The transformation of matter is a real important part. Matter doesn't just stay as it is. It goes through lots of transitions. And water, again, is a good example because we're used to all phases of water around us. So liquid water comes out of the sink, all right, and you can drink it right on. But if it's a hot day, you might want to have an ice cube, all right? And ice is just solid water. So you put the ice cube in your liquid water to cool it down. On the other hand, if it's a cold day, you might prefer like a cup of tea or my favorite, coffee, but we don't have to go there. Anyway, you might want to have a warmer version. And so in the process, you've got to turn some of your liquid water to steam. Steam is gaseous water. So transforming liquid to solid, ice, or liquid to steam, gas is really important. And this is how chemists roll, all right? We're always interested in these kind of transformations. Some, it'll take a lot of energy to make them happen. Some you actually get energy out when it happens, but knowing how it's going to change is part of chemistry.
Matter interacts with other matter and is transformed. Life is perhaps the most complex expression of chemical interaction. Living things transform matter to further their own being. They are transformations of matter. Life radically changed the chemistry of Earth and its atmosphere. 70% of the oxygen in the air is produced by microscopic plants in the oceans, and the rest comes from land plants. Complete understanding of the chemistry of even the simplest forms of life is beyond our present comprehension.
So earlier I mentioned coffee, and if you ever get to know me in person, I love coffee. I drink way too much and stuff like that. It's one of my weaknesses. However, I do it because caffeine is, first of all, I do enjoy the taste, but really I like the caffeine. All right, the caffeine is wonderful. It kind of keeps me stimulated when I need a little extra energy if I'm in front of people or whatever. It's just something I like, all right? I am interacting with the caffeine, all right? The caffeine comes in my body. It does some kind of transformation. I have a little bit more energy, and Dr. Michael is happy. But anyway, that's a very silly and cheesy example of how this works. There's lots of examples of this around us all the time. If you see a plant grow, or you see a piece of sodium metal reacting with water, that's the matter interacting with itself. And that's also where, of course, a lot of the energy part comes from and stuff. So knowing even how the simplest life functions is beyond scientists right now. It's like way too complicated. However, we have like bits and pieces and stuff we start to figure out, and chemists are always interested in making our understanding of how the matter forms interact that much better.
Chemistry is the science of matter and of its transformations. The equipment this diver wears allows him to breathe underwater for a very long time. The carbon dioxide he exhales reacts with chemicals in his apparatus to produce oxygen, which he can then rebreathe. This diver can explore the sea with greater freedom because chemists have helped develop every piece of equipment he uses. Chemists press the frontiers of knowledge in laboratories and offices with test tubes and computers. In the pursuit of the practical, they too are explorers.
So chemistry is very important, and we're going to see lots of examples, not only in Chem 221, but all the way through Chem 223, of how important chemistry is. And it affects all parts of our lives, from the food we eat to the chemicals we use, the computers or cell phones that you might be using to watch this right now. Everything around us has some aspect of chemistry. And so understanding how these things interact is the big important part of being a chemist.
People make molecules for all kinds of reasons. One of them is that a molecule is beautiful. That, for instance, is the case with this fantastic platonic polyhedron, as it's called, of dodecahedrane, with 20 carbon atoms in it, with 12 faces, all pentagons. This was made not too long ago by a friend of mine at Ohio State, Leo Paquette. Now, he made it because it was a goal, a mountain to be climbed. Many people had tried, no one had made it, and it's aesthetically pleasing in its symmetry. You see this gracefully curving triple helix. Now, this structure has not been made. What I see is that it's pretty, it's beautiful.
Chemistry is very important to so many things around us. However, if you think that I'm going to say, oh, chemistry is more important than anything, no way, absolutely not. And here's a great example of chemistry and art. Now, this guy that just gave that presentation, Dr. Hoffman, he's a fantastic chemist. He won the Nobel Prize in Chemistry in 1981, something called the isolobal analogy, which we might talk about in Chem 222. And he's very brilliant. And as a chemist, I have the highest regard for him. However, he also has done some art, and he talks about things being beautiful and pretty and stuff like that. And I don't know, that's never really quite gelled with me. Here's an example. He created some poems, and here's a quote from one of them. There was no question that the reaction worked, but transient colors were seen in the slurry of sodium methoxide and dichloromethane, and we got a whole lot of products for which we can't sort out the kinetics. The next slide will show the most important apart very rapidly within 2 minutes. And I forgot to say, on further warming, we get, in fact, the ketone. Well, that doesn't sound exactly like Walt Whitman to me, so I don't know if he's exactly the best thing. I definitely encourage Dr. Hoffman to stick with his chemistry, which is literally beautiful once you see it, but art and chemistry, I don't know. He actually had a play, Oxygen, that was primarily performed in Washington, D.C., but, well, anyway, you can do it if you want to. So, chemistry and art, maybe, maybe not. However, we should talk about some other famous chemists, some of these that you might have actually heard of. Dr. Hoffman is really popular in chemistry circles, but maybe not in other ones. Dolph Lundgren is my favorite chemist, I think, of all time. He has a MS, Master's in Chemistry, and he was an actor. He's been in Expendables 2. He was in Rocky 4 and several other movies. I've always had a weakness for Dolph Lundgren. Red Scorpion, if you know about these things. I have a lot of bad movie references. I'm so sorry. More famous, maybe even than that, though, Margaret Thatcher, all right, Prime Minister of England for a long time. She has a bachelor's in chemistry, which is pretty cool. And her politics, whatever you feel, is fine. But anyway, she was a chemist, and that's pretty cool. And even Pope Francis, amazingly, has a master's in chemistry. And that's kind of cool, too. Now, all of these people obviously are using their skills in other directions, probably away from chemistry, but I'm sure the chemistry helped them to get there and stuff. Anyway, now you know other famous chemists. Okay, let's talk about chemistry a little bit more. Chemistry is a big subject, all right? It's a whole series of classes and stuff you can take. And when people think about all the chemistry that's known, they break it down into different branches of chemistry. And the chemistry branch you may or may not have heard of, but it's probably the most famous, is organic chemistry. Organic chemistry is the study of chemistry that's mostly focused on a very select few number of elements. Carbon, nitrogen, oxygen, hydrogen a lot of times, sometimes a few other ones, but a very small select group. After the Chemistry 221 through Chemistry 223 series, the next chemistry class that you would take, if this is your path, would be organic chemistry. At Mount Hood, that's Chemistry 241 through Chemistry 243. So you'd get deep and hardcore into those couple of elements, which is really cool. At Mount Hood Community College, we have 2 organic chemists on the full-time faculty, so it's a pretty common kind of thing. I'm biased, though, because I am not an organic chemist. I am an inorganic chemist. And the reason I chose inorganic chemist is because basically it has metals in it, and metals have beautiful colors. I love color. It's a long story, but anyway, seeing color is really cool. I wear all black, basically, but I really, really dig seeing color. And in a laboratory, the metals have just breathtakingly cool colors. We'll talk about it. Inorganic chemistry is basically everything that's not carbon. Even that's not right, because there is some carbon, but it's mostly about the metals, all the elements basically not in the organic chemistry, which is quite a few of them. Inorganic and organic do share a lot of similarities. Inorganic is also a big thing, although organic chemistry is much bigger. At Mount Hood Community College, we have 2 full-time inorganic chemists, myself and one other person, so it's kind of cool. We're the metal people. Analytical, physical, and biochemistry are 3 other branches of chemistry. Analytical is really important, and all the branches use this to a point. Analytical is about answering the questions of how much or what kind of things you have. Spectroscopy, which is the use of light and chemicals, is a big part of analytical chemistry. And even though I'm an inorganic chemist, I did a lot of analytical techniques while I was doing my research and stuff, which is cool. And all people do that. All chemists do it. Physical chemistry is where physics, chemistry, and arguably calculus meet together. They try and model different behaviors of gases or liquids and stuff like that in the real world. It's basically a big measurement part too, a little bit analytical, but it's a really interesting field. If you like physics and calculus, then physical chemistry is the area you want to go to, and that's totally cool. The newest branch, arguably, on the block is biochemistry. biochemistry or biochemical chemistry. Biochemistry is where biology and chemistry meets. It's the chemistry of life. And at Mount Hood Community College, we do have one full-time biochemist on our faculty staff and stuff, which is cool. Biochemistry is the new and upcoming and probably the most popular branch right now. Traditionally, organic has been bigger, but now biochemistry is probably becoming even more popular. And again, all of them bleed over together. These are artificial kind of divisions and stuff, so you're going to see different kinds. There's lots of other ones, though, too, and I'm just going to put this slide up here to show them. Some of these are pretty obvious. Some of them are maybe not. Geology is, of course, a big-time part of chemistry. Physics and nuclear science, so radiations goes together. All of the forensic studies, so if you watch crime shows and stuff, a lot of the forensic stuff, of course, is based on chemistry. Chemical engineering is a big part. One that's not on this list, I would argue, is astronomy. Astrochemistry is a big part of everything. So there's lots of different types of chemistry and lots of uses for chemistry. And that's why people like even Dolph Lundgren and Pope Francis, they were able to find paths to go on after chemistry and stuff that may not have been obvious right now. Environmental chemistry, of course, very important too. Got to keep the earth clean, et cetera, et cetera. So when it comes to chemistry, we need to start learning the language of chemistry. And this is going to be a topic we'll go on here in the first couple lectures. So I like to use the idea of language to explain how chemistry works. And in the English language, there are 26 letters, and those 26 letters make up all of the words. So like the words I'm using right now. And chemistry has something very similar. Chemistry has elements, and elements are kind of like the letters of the English language. They're the smallest pieces. In chemistry, these are these cannot be decomposed by ordinary means to other substances, so they're literally like the building blocks of everything around it. Sometimes I like to think of elements as like little pieces of Lego, and there's different types of Legos, all right, but the Legos together make really ornate kind of models. Elements can also come together to make beautiful combinations of things like sugar, caffeine, here we go again. Sorry, I'll try not to stay focused on caffeine, but anyway, caffeine, all those different kinds of DNA, all right, et cetera, et cetera. Here's just some examples of some of the elements. Sodium is an element. Aluminum is an element as well, and bromine, and there's lots of examples. And all of these are literally the smallest pieces of everything around us, all right? And I mean that literally. So the air you're breathing to the cell phone, which is a common thing and stuff, all of them have elements inside them. This guy, Lavoisier, was the first one to describe element for literally a chemical element. He thought that there were like small building blocks that make up everything else. We'll talk about Lavoisier more, but it is kind of cool. He was the one that first apparently used the idea of an element to describe the language of chemistry. Now, on the periodic table, you see lots of different symbols. Sometimes the periodic table will have the names under them, but the important thing is that the periodic table, that is the list of elements. Those are literally the letters of my alphabet in chemistry, all right? And if there are 26 letters in the English language that makes all the words I'm using, imagine what 118 letters could do in terms of making words, compounds, and stuff like that later on. So this is my alphabet, all right? And the periodic table is so important. It's a great cheat sheet we're going to see, really helpful. This guy Berzelius was the first person to use symbols for the atoms. So instead of writing out hydrogen all the time, you could have just H, all right? And instead of having lithium, you would have Li, et cetera, et cetera. Now, currently, there are 118 elements on the periodic table. That number has changed just while I've been teaching at Mount Hood Community College, all right? Several of them have appeared over the last decade or so, and I expect it to change in the future as well. Periodic tables will constantly go in, they'll be like working, and then they'll be out of date really soon. So it's important stuff to kind of stay on top of it. The only elements that were known pre-biblical times are the ones listed there: the sun, the moon, the Venus, etc., stands for gold, silver, copper. All right. Iron was iron. Fe was Mars. Tin was Jupiter. Tin is Sn, by the way. Pb, which is lead, Saturn. Hg, Mercury. Sulfur and carbon, although they were called different things. So we've come a long way since the pre-biblical times, which you can probably imagine. Pretty exciting, and we'll see some of the things we've discovered since then. The first person to propose the idea of the periodic table was Mendeleev. He was really awesome, and he realized that some of the elements had repeatable properties. And so you can see the early version there of the periodic table. It was listed by mass, and we'll talk about mass later, and then also what it is now, which is atomic number. But it was the first time that someone thought, hey, maybe there's some kind of method to the madness, like there's a pattern involved, and that's pretty cool. Mendeleev is given a lot of credit because he predicted the elements gallium, germanium, scandium, and technetium, those four listed at the bottom there, before they were known. And later on, they did actually discover them. Pretty cool. Good job, Mendeleev. So that's the old periodic table. And notice there's rows and groups. Of course, the new version looks a lot different. The new version is split, and we'll talk about why the periodic table looks as it is. You'll notice on this periodic table, elements 113 through 118, kind of in the lower right, are not showing. At the time this periodic table was made, those weren't around. So this periodic table is out of date. Terrible, terrible, bad instructor. But you'll see this. It's really common and stuff. Anyway, this periodic table is a little bit different too. It's got some cool color coordination on it. The yellow, kind of off yellow colors, those are metals. The blue elements are called nonmetals, and the green ones in the middle there, metalloids. So first of all, note there's a lot more metals than there are nonmetals or metalloids. So most of the periodic table is made of metals. Metals generally like to give up electrons. They like to conduct electricity and heat. Nonmetals generally will take the electrons. They don't conduct electricity. Sometimes they'll react with each other. And a metalloid has properties of both metals and nonmetals. And we'll talk about this more here coming up. But start thinking about metals, nonmetals, metalloids, a lot more metals on the periodic table than nonmetals, but we're going to see those nonmetals super important for chemists. And if you're really into the periodic table, you can make a periodic table. Yeah, I know, keep my day job. Anyway, again, notice that this periodic table is also missing a lot of elements, so this person's periodic table is out of date. The problems 21st century people have.
If you were to ask me to summarize on one sheet of paper all the potential things that could happen in chemistry, not only in chemistry, but in all fields of science, physical science that is, and maybe in engineering, the one sheet of paper I'd give you would be the periodic table. That's everything we ever will do in science is summarized here. All the compounds that we'll ever make will come just from combining these elements, these 100-odd elements on this one sheet of paper. The number of compounds that could be made potentially out of this are practically countless. We now know of maybe 10 million compounds, but with only perhaps 5 elements, thinking of the ways we could combine them, we could potentially make 10 billion compounds. So if we were to combine many, many elements from the periodic table, the number becomes absolutely enormous.
I love this video. He says how there's about 10 million compounds, but most of them with just 5 elements. And what he's referring to there is organic chemistry. Organic chemistry, which has been studied a lot because it's super important. It's about life and stuff like that. And, people like to live. But anyway, it's about organic chemistry. And with those basically 5 elements, most of the 10 million compounds have come from them. But there's more in just those 5 elements. And we'll see this in Chem 222. Those 5 elements are incredibly versatile. So we could make many, many more compounds just from those 5. And that doesn't include the other 100 plus elements, which aren't those 5 elements. So the number of compounds possible to chemists, virtually limitless, all right? And we've just begun to kind of get into how these things are made. And there's more and more different variations and stuff. It's really cool. So there is a lot of work left to be done in chemistry. We have just barely scratched the surface. And in the upcoming decades, I think chemistry is going to become even more important as we go through problems with the environment or we start exploring space and stuff like that. All these things, super important. Here's an example of how important chemistry is. And of course, this goes back to the cell phone. And I've mentioned this several times. But most cell phones have about 1/3 of the naturally occurring elements used inside them somewhere. All right. So the case has some polymers and also a couple of metals. The processor has a whole bunch of different things. A lot of the processors in a cell phone have a little bit of gold in them, which is really cool. The screen has silicon with different metals. The batteries, of course, lithium batteries mostly, a little bit of other types of metals in there. So your cell phone is a testament to the powers of chemistry. And everybody, of course, wants, better cell phones, blah, blah, blah. Well, chemistry is going to be the way to get there and stuff. And engineering, of course, too. I'm not trying to disrespect any other science, but chemistry is absolutely going to be important in figuring out how to make even better cell phones, stuff like that. An atom is the smallest particle of an element that still has the properties of the element. And this is kind of cool. So if you take like a whole bunch of gold and you cut it in half, though the half is still going to be gold. You take that half and you cut it in half. So you're down to 1/4, still going to be gold. And then you get down to 1/8 and 1/16 and it's still gold, 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 gold. But finally, you're going to get down to something which is so small. And if you cut that in half, it's not going to be gold anymore. And that's something that you can't cut in half is called an atom. If you cut an atom of gold, it's not going to be gold anymore. It's going to be something else. And that's difficult to do, but it is not impossible. So literally, atoms are the building blocks of elements. They're the smallest pieces, the individual Legos that go into making different things, all right? And they are so small. These are examples of home movies and pictures, if you will, of atoms, all right? The left-hand side, the animation, is a carbon set of carbon atoms, all right? The right-hand side, those little humps are all representing copper atoms, all right? And the distance is very, very small. Distance across is about 1.8 nanometers for the copper atoms. Now, a nanometer is 10 to the -9 meters. It's a really small length, and that's what we're dealing with here. This is smaller than, for example, like most microscopes. Microscopes use micrometers or micrometers, which are 10 to the -6 meters, even bigger. So chemists have to use really special techniques even to get little pictures like this, which is cool. The atom has a shape now that's been discovered through time that looks something like this. And you can see, first of all, it's basically like a sphere, like a circle. Three-dimensional circle is a sphere. And those shimmering things around it, that's called the electron cloud. And the electrons kind of shimmer around. And then inside the middle of the atom, which is kind of a red and green thing, that's the nucleus. The nucleus of the atom holds what's called protons and neutrons. And electrons kind of quote-unquote circle around the outside. So the atom more or less looks like this. It's basically a small sphere. All right, most of it is just the electrons, and in that middle is the nucleus where the protons and the neutrons are. And we're going to talk a lot more about this in the next chapter. Now, if you want to do something with your elements and you want to make something arguably interesting, like caffeine, here we go again. Anyway, you're going to have to make what's called a compound. So a compound is just a mixture of atoms in a specific ratio to make something more interesting. And the compound there on the left, the red compound in the blue liquid, all right, that red compound involves something called dimethylglyoxime, and you don't need to know that. I abbreviate it DMG because it's too many things to say. But anyway, DMG is the red compound, and that DMG, the little picture of it, is right there. Now, this picture here is a model, all right? Atoms are so small that chemists use models to describe what they look like and how they're oriented in space. And a lot of times the models are color coordinated. So the red atoms are oxygen, the one in the center right there, that's actually a nickel. The black atoms are carbons, the little white is hydrogens, and the blue is nitrogens. This is the compound you're actually going to make in Chem 223 if we have face-to-face labs. Dimethylglyoxime and nickel is a good test to see if you have nickel in your solution, but we'll talk about that later. So this is an example of a compound. This compound has nickel, carbon, hydrogen, oxygen, and nitrogen atoms in it. So many atoms make a compound, which is cool. If this was a regular lecture, I have what I call iClicker questions. And iClicker questions are just a great way for people watching my lectures to hopefully stay engaged. And I would offer them a little extra credit and stuff for participating and stuff like that. It's cool. You watching this video right now, you don't have the opportunity for an iClicker. I apologize. I'm not that tech savvy, I guess, to do it. However, we are going to go through these iClicker questions because it's a great way to test your knowledge and see how you're doing with the concepts. So this is going to be the first of these iClicker-like questions. They would be live if this was an actual lecture, but for this recorded lecture, you can just test yourself to make sure that you understand the answer. So some of these questions will have small calculations. Some of them will be just conceptual to see what's going on. Let's look and see how this works out. So this first iClicker question says, which of the following is not a compound? All right, and there are 5 possibilities. Now, remembering that a compound is a mixture of different types of atoms, if you look through there, the first one, table salt, is sodium chloride. That has Na and Cl, sodium and chlorine. That's a compound. The next one, water, is H2O, all right? Water has hydrogen and oxygen, 2 types of elements. That's a compound. But if you look at the next one, potassium, potassium has only 1 type of element, potassium, which is K. Potassium is an element. It's one of the pieces on the periodic table, and there's nothing else with the potassium. So potassium is not a compound, all right? It's an element on the periodic table, but it's not a compound. The next 2 examples, table sugar and drinking alcohol, both have carbon, hydrogen, and oxygen. So those would also be compounds. Only potassium has just 1 element. So that's why potassium is not a compound, it's an element. And basically in chemistry, we're going to look at compounds and elements and see how they interact. Elements make compounds. You can break a compound down into the element if you're tricky. This compound on the left that I circled with the nickel, carbon, hydrogen, oxygen, and nitrogen is called an ionic compound. It has a metal, nickel, with a bunch of nonmetals. The CH, O, and N are all nonmetals. And ionic compounds have unshared electrons, and that's going to be important to us later on. Caffeine, there on the right, circling. Oh, beautiful caffeine. I need more coffee. Okay, sorry, Russell having a spaz. Caffeine and water, H2O, are examples of compounds made up exclusively of nonmetals, all right? There's no metals in water or caffeine. If you look back at that original thing, hydrogen, oxygen for water, or carbon, hydrogen, nitrogen, oxygen for caffeine, those are all in the nonmetal parts. So that's going to be a different kind. A molecule is the smallest piece of a compound that has the same properties of the compound. And so as an example of that, if you've ever had or seen like pure caffeine, sometimes you can see it and stuff and almost in no-dos and stuff like that. But anyway, if you had a whole bunch of caffeine and you broke that down in half, you'd still have caffeine, but you'd finally get down to a molecule of caffeine. And if you break the molecule apart, you can make elements or simpler compounds, but you wouldn't have caffeine anymore. So a molecule is the smallest piece of the compound that still has the properties, all right? After you break apart the molecule, it won't be the same. It wouldn't be caffeine anymore. H2O and that C8H10N4O2 thing, those are molecular formulas, and they show the numbers of atoms and also what types of atoms. So water has 2 hydrogens and 1 oxygen. And notice it's not H2O1. It's just H2O. Chemists don't put a 1 there unless if it was 0, the oxygen wouldn't be there. Okay, so not having a number means that it's 1. Caffeine has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. So those are different because they have different types of atoms and different numbers of atoms. If you have a compound like water or caffeine earlier with all nonmetals, then you're going to have what's called a covalent compound. And a covalent compound has shared electrons. We're going to see that there's differences between ionic compounds, where you have metals and nonmetals, and covalent compounds like this one, which are made of nonmetals. We'll talk more about that in future lectures. Gold and mercury to us look quite different. Like gold's like a chunky kind of metal, and mercury, which is sometimes called quicksilver, mercury is a liquid. All right, it's kind of fun to look at, but it's also very dangerous, so be careful. On the other hand, those things that are rotating there, those are the ways that gold and mercury are related on the atomic level. And you can see they look very similar. So chemists are always interested in the nature of matter and how it relates to the atoms and the molecules. And on this example, the atomic level looks quite similar, but in the real world, the pictures on the upper left, the atoms look a lot different. The elements look a lot different. As a chemist, you have to be thinking about what I call the macroscopic world, and that's the world we use to interpret through our eyes, all right? Gold looks different than mercury, all right? No problem. Water looks different than table salt, absolutely, all right? However, as a chemist, we're going to think about things on the atomic level as well, and that's what those rotating things are for gold and mercury, and we'll talk about those in Chem 222. But on the atomic level, they look very similar. On the macroscopic world, gold and mercury look quite different, and we can use symbols, i.e. those element symbols and stuff like that, to represent these things to each other, so we can talk about them and figure out what's going on, stuff like that.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light.
So in this video, you actually got to see a balloon filled with hydrogen gas basically burned, all right? And the burning is just there to add some oxygen. And it adds oxygen to the hydrogen to make water. And there's a lot of energy released, all right? The balloon went boom. Sound effects not necessary, all right? Anyway, so in the macroscopic world, you light a balloon filled with hydrogen, makes a bam. Okay, cool. On the atomic level, all right, the hydrogen, which are little white molecules there together. They're represented by those pieces right here and right there and right there. Those are H2 molecules, or hydrogen, all right? And the oxygen, which is around us all the time, is represented by those two little red atom kind of combinations floating around. And basically the match, the light, just like starts the party, and at the end of the day then, it makes water, H2O. So you can see that water, H2O, would have 2 white hydrogens and 1 red oxygen, and we'll talk more about this formation here pretty soon. But on the atomic level, that's what's happening. The H2 in the balloon reacts with the O2 on the outside of the balloon to make water at the end, the H2O molecules that you see. Now, that took a lot of words, and chemists can be very lazy. So it's also nice to think about it from a symbolic perspective, i.e., how can we write this? And that's what this thing is right here. This is a balanced chemical reaction, and we'll talk about this later on in Chem 221. But what it's saying is that you're taking 2 of those red H2s, and it's a gas, plus 1 of the O2s, the red ones that are gas too, and you're going to make 2 waters, 2 H2O. And this is gaseous water. The G stands for gas. All right, you could, if you cooled it down, have liquid water or something like that, but right now it's gas. So all of these perspectives, super important when it comes to chemistry. This leads us more into what solids, liquids, and gases are all about. And this is a really interesting part of chemistry as well. All substances, arguably, can have solid, liquid, and gas phases. Solids have very rigid shapes. They're very fixed volumes. And chemists understand solids pretty well. And you are around solids all the time. Table salt or sugar, table sugar are great examples of this. There are also things like, iron and things like that are around. The solids are really good, but you can't really pour a solid. The volume is fixed, all right? So solids have some uses for them, but also some weirdness too. Now, a liquid, on the other hand, you can pour. It doesn't have a fixed shape, all right? It will fill a container completely. Like if you pour solid into a container, you'll have like little places where it kind of makes little holes and stuff like that. Liquids don't have that. Liquids are really important, of course, water being the most important of all of them, but liquids are arguably not well understood. It's very hard to predict something that's so dynamic and moves around all the time. Gases, on the other hand, are another phase of matter. They will expand to fill their container, and if you give them enough time, they'll be consistent about it. Gases is actually where chemistry started, and chemists have a very good understanding of how gases work. We'll talk more about this in Chem 222 when we talk about gases, but it's amazing that gases, which are so hard to control, are actually pretty well understood. Now, just to be fair, there is a fourth and very important phase of matter called plasma. And plasma in the universe is the most important. But in the Earth, in our world of day-to-day kind of things, solids, liquids, and gases dominate. So we won't talk about plasma until Chem 222, but just keep that in the back of your mind, man. These things can be pretty cool.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
The kinetic nature of matter comes from what's called the kinetic molecular theory, and the KMT for short, which is what I use because I don't want to use a lot of syllables. But anyway, the KMT is the way that chemists think about it. So you can see that each of those solid, liquid, gas boxes there, they have some kind of atom or molecule, doesn't matter, but that's what they are. In the solid phase then, those molecules are pretty tight together. They're held pretty tightly together. But if you add a little bit of energy, you can arguably turn them into a liquid where there still is consistency between the molecules, but it's not as strong as solids. Like liquids will flow, solids don't usually flow. On the other hand, you add even more energy, gases have no interaction with each other at all. They're almost like independent little entities. So the gases and stuff, you have to have something contain them or else it's really crazy. We'll talk about the KMT with phases of matter as we go through this course, but I'm introducing it now just to let you know that's what chemists use right now anyway as the idea of how solids are different than liquids and liquids are different from gases. You have to know how to turn one phase of matter into the other. So the energy of transitions is really important to scientists. And I have down there the three phases. The lower left is solid or ice, or in this case looks like snow more than ice. The lower right is a liquid water. All right, so you can see the liquid on it. And the upper right, the steam over the lake, that's like gaseous water. All of them are water. They're all H2O. But the question is, how do you go from solid to liquid or liquid to gas? Anytime you go from solid to liquid or liquid to gas, it's going to take energy to make those transitions possible. They don't just happen by themselves. And chemists refer to this as an endothermic transition. So endothermic means that it takes energy to happen. So solids to liquids, liquids to gas, always endothermic. On the other hand, if you go gas to liquid or liquid to solid, you're going to see that you actually end up releasing energy. And if you release energy, chemists call that kind of transformation exothermic. So this slide right here is basically introducing the terms endothermic and exothermic. Endothermic means it takes energy to happen. Exothermic means you're going to get energy out to make it happen. Now, in the middle part right here, you can see there's like a solid, there's a liquid, and there's a gas line. I guess I said solid first, but you get the idea, all right? Anyway, blah, blah, blah. Anyway, this is an energy axis, all right? So you can see that going from a solid to a gas, which is this first arrow right here, which is called sublimation, by the way, that's endothermic. It's going to take energy. The higher state is a higher energy than the lower, so you're going to have to add energy to make it happen. On the other hand, if you go from the gas to the liquid through the process of condensation, the energy goes down. Those are going to be exothermic. The lower state, the final state is lower in energy than the initial state, so energy was released. Also, freezing is the same thing. You're going from higher liquid energy to a lower solid energy. These will be important to us later on, but really for right now, what I want you to just hear is endo and exothermic. And endothermic means it needs energy to happen. Exothermic means you're going to get energy out when it happens. Physical properties are important when you want to identify a compound that you may not be totally sure what it is. And a physical property is pretty cool. It's a type of measurement that doesn't change the substance itself. So for example, if you look at that bromine right there, it's kind of a brown-red color. That's the color, all right? And looking at the color doesn't change the fact that it's bromine, all right? If you wanted to know more about bromine, you could take a melting point or a boiling point, which is something a chemist can do, but you're not going to destroy the sample. You could still use it. Also, the odor of chemicals sometimes is considered a physical property because odor is something that you could really redo. Physical changes, then, are things that are related to the physical property. So if you boil that liquid, that's a boiling point measurement, by the way, that would be a physical change. You could melt a solid, all right, solid to liquid would be a physical change. You can also take a solid and put it in a liquid, and if it makes a mixture, what's called a homogeneous mixture, which just means one phase, it doesn't look like a rock in a water, it looks like it's just one thing, that makes a solution. And a solution is a physical change. We'll talk about these later too, but a physical property is a way that chemists can figure out what a compound is without destroying the compound itself. And believe it or not, that's kind of useful sometimes. Which of the following is not a physical change? Now remember, physical change, it's reversible, all right? So freezing of a liquid to form a solid, I think we could take that solid and make it a liquid again. So that should be something that's reversible. I think that's going to be a physical change, all right? We can redo it if we want to. B, it says dissolving a solid in water form a solution. That was that last little blurb there at the end. In theory, if you took a solid like sodium chloride, table salt, and put it in water, you could evaporate the water to get the table salt back again. So that is also reversible. So that's not a problem. That is a physical change that doesn't count here. The next one, evaporating liquid water into steam. Well, we could take that steam and collect it, turn it back into liquid water. That's reversible. That's no problem. So that wouldn't qualify here. However, the next one, if you take a piece of paper and you burn it, all right, that's kind of fun to do. But if you think, oops, I needed that paper back, it's, I would argue, impossible or pretty gosh darn close to impossible to get that ash back to the original place that the piece of paper was. So that is not a reversible process. D is definitely not a physical change, all right? We can't reverse it. The last one, if you take ice, solid water, and turn it to vapor, like gaseous water, yeah, you can reverse that one. But there's no way that you're going to take ash and turn it back to your original piece of paper. That's going to be, we're going to see here, a chemical change where you have actually transformations at the chemical level happening. Speaking of chemical change, physical properties are really cool because they can help you identify compounds, but physical things are reversible and they're really important. But sometimes you need chemical changes too, the way that chemicals react with one another. But just realize that if you do one of these, it's going to be really difficult to get it back to the original form, hence the burning of paper earlier. Physical properties, again, don't change the composition. Chemical properties do. So in the upper one, you've got a little magnet there attracting paper clips. All right, that's a physical property. All right, you can get the paper clip off, no problem. On the other hand, poor Coyote down there, after being with a Roadrunner, his TNT goes off. I'm amazed he's still there. But anyway, that's obviously a chemical property. All right, you can't take the TNT and get it back to TNT after you've exploded it. It would be all gone stuff. Terrible. Terrible. Physical properties are great for separating compounds, and that includes things like density. Density, we'll see in a little bit, is the relationship between mass and the volume of an object. There's also melting and boiling points, and in the last example, we even saw magnetism, which is another way to measure it. So all of these are great ways to tell what your compound is, what your element is, and stuff like that. However, if you're going to do physical properties or physical measurements on a chemical compound, you have to have some kind of unit, all right? And units need a system in place scientists can talk to each other. And in chemistry, like all of science, you really should use what's called the metric system. Now, on the little slide that's showing right there, the green countries in the top graph are all countries that use the metric system by default, all right? And it's no problem. And you can see that most of the world uses the metric system. The lower one, though, shows countries, which are in red, which use the quote-unquote imperial, or what I'll call the English or American set of units. And unfortunately, the United States is one of them. So there's a lot of times a translation problem of units between groups working in America and groups working in basically everywhere but America. A couple countries use it, but boy, not many of them. So the metric system, if you've already had exposure to it, is super, super cool and easy to use. On the other hand, if you haven't used it, I'm going to show you how super cool and easy it is with a couple of examples. So just hang on. This is just a silly joke. The real reason the United States is reluctant to make the switch to the metric system, miles Davis versus kilometer Davis. So first of all, miles and kilometers are both units of length, all right? And a mile is longer than a kilometer. So you can see that the miles Davis version is bigger than the kilometer Davis. Miles Davis is one of the premier jazz people from the 50s and 60s, 70s. He's really cool. His music is incredible. This is a joke about Miles Davis. There is no kilometer Davis, but because a mile is longer. All right. I have a strange sense of humor. You can just bypass this part of the video if it makes it more sense. Oh, let's have some more jokes. What the heck? Left one is peanuts. A centimeter? If any centimeters come crawling in this room, I'll step on them. And then you can about hear the teacher going, wah, 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 wah. And she goes, yes, ma'am. So poor Sally got in trouble. Centimeters aren't little bugs to squish. They're actually a really useful tool. But anyway, I digress. And then on the right, then this guy says, I got you 10 roses. He thinks strong relationships are based on the metric system. So, of course, the traditional way of buying roses is a dozen roses, which is 12, but metrics we're going to see is based on 10. So he was being a little cheap there maybe, but still the point is good. Hopefully the significant other is not disappointed. Anyway, doesn't matter. But metric system, super cool. I promise. It's really neat. Once you use it, it's really cool. Now, I was born in Gresham, Oregon. Okay, so I grew up on feet and miles and all that kind of stuff. And I'll think, when I think of temperature, a lot of times I think in Fahrenheit. However, as a scientist, it's very, very helpful to think in meters and to think in grams and to think in kilometers and stuff. So I have a science mind and my Gresham, Oregon mind, and they are not incompatible. You can translate from one to the other. Just realize that here in science, we're going to use the metric system big time. Here's an example of how a metric problem might happen. If you've done metrics before, this shouldn't be too bad, but if you haven't, this will be tougher. And it says, place the following in order of increasing size. And there's 215 millimeters, 9 centimeters, 2.3 meters, and 0.125 meters. So it says put them in order of increasing size, smallest to largest, okay? Metric system is based on these prefixes, and that's what I'm throwing at you here. And we're looking at two of the prefixes. We're looking at a centa and a milli, little c and little m. And there are 100 centimeters in a meter, and there are 1,000 millimeters in a meter. So I think we can all agree that of those, like a 2.3 meters would be bigger than 0.125 meters, all right? So 1.125 has to be to the left of the 2.3. But the question is, how do the other ones relate? So 215 millimeters, and there are 1,000 millimeters per 1 meter. You would take 215 and divide by 1,000. 0.215 meters is what 215 millimeters is. And that number is bigger than 0.125 meters, but not, of course, 2.3 meters. So far, we've seen that 0.125 is small. 215 millimeters, which is 0.215 meters, would be next, and 2.3 meters would be the biggest. But we still need to talk about 9 centimeters. So to convert centimeters to meters, you divide 9 by 100. 9 divided by 100 is 0.09. 0.09 meters is smaller than all the other ones we saw. So in this problem, 9 centimeters is smaller than 0.125 meters, and that's smaller than 215 millimeters, which is 0.215 meters. And that's smaller than 2.3 meters. So this problem, if you're totally like, what the? Don't worry about it, okay? I am introducing how important the metric prefixes are, centa and milli, and there's a couple other ones. And you've got to know how to convert from one to the other, because we'll do these kind of things in lab and in theoretical kind of things. Think about this problem, and we'll see later on some better ways how to do this kind of stuff. There are many metric prefixes, and a lot of them you probably use all the time. In computers, a megabyte and a gigabyte and terabytes, those are all examples of metric prefixes used for some metrics. In chemistry, we don't use those as much, but here are the 5 metric conversions that you've really got to know for this class. And the 5 are called the kilo, the centa, the milli, the micro, and the nano. And you can see that each of them have a letter associated with it. So kilo is K, centa we saw earlier was C, milli we saw earlier was M, micro is a little Greek mu, it's like a U with a longer line on the front of it, and nano is N. And all of those have a conversion number that's associated with it. So a kilometer is 10 to the third meters. 10 to the third is 1,000. Notice that centa is 10 to the minus 2 meters, if it's centimeters. The nanometer, 10 to the minus 9 meters, etc., etc. And knowing how to convert one of those is really important. A nanometer is very, very, very small, all right? It's 10 to the minus 9 meters. On the other hand, a kilometer is really big. That's 10 to the third or 1,000 meters. So it's kind of cool to put these all in perspective and stuff, how they work out. Here's an example of the utility of this stuff. The distance between the oxygen and hydrogen in water is about 9.4 times 10 to the minus 11th meters, and that's a really small distance. If we were to talk about that in centimeters, which people do in their day-to-day world, 9.4 times 10 to the minus 9, and that's better, but still a little awkward. In biology, a lot of the stuff is around the micrometer or micrometer. And if you convert that meters into micrometers, it's 9.4 times 10 to the minus 5. But what chemists will usually do is use the nanometer, or sometimes even smaller units. It's 0.094 nanometers. And you can imagine that if you're going to write this out, writing 0.094 nm is a lot easier than 9.4 times 10 to the minus 11th meters. So that's one of the reasons why chemists do these kind of things. Certain types of measurements equate themselves better with certain types of metric prefixes. The metric prefixes are all over. A terabyte is tera, giga is G, mega, kilo, hecta, deca, deci, centa, milli, micro, nano, pico, femto, et cetera, et cetera. So again, the ones we're going to use here, nano, micro, milli, centa, and kilo. Those are the 5. And they're super valuable. Also, what's really important is that all of those metric prefixes have a number associated with it. So like kilo is 10 to the 3rd, and micro, as we saw earlier, 10 to the minus 6. So we can use those and stuff in order to figure out how these all work out. Very important, all right? If you come to a thing like this and you're dying of water and you've got water 9 km or water 50 meters, oh, well, 50 is a lot bigger than 9. I better go for the smaller number 9. But see, 50 meters, if you converted that to kilometers, you would divide by 1,000. So 50 divided by 1,000 is much smaller than 9. So this poor person's going to have to crawl a lot farther to get to water than if they went left where it's only 50 meters. So, woohoo! So make sure you know this if you're ever out in the desert and thirsty. And as I said, my sense of humor is very strange.